Okay, so can everybody hear me? Yeah? Okay, so I was asked to talk about string compactifications. And of course, string compactification is a huge subject. There's no way I could do justice to it just in the next few lectures. So we're going to concentrate on a few special topics which nevertheless cover a broad swath of the possible constructions and which give you some general overview of the techniques that are available for studying string compactifications. So today we're mostly going to focus on the heterotic strings, heterotic compactifications, with a little bit of overflow into tomorrow. Tomorrow then we have a brief discussion on perturbative type 2b. And finally we'll give a discussion of F-theory, and we'll see how structures in F-theory generalize the various structures that we encounter in heterotic compactifications and in perturbative type 2b compactifications. Now, we have a huge audience, and with a huge audience comes a very large diversity in the backgrounds that people will have. So I understand that some of you will have worked on string compactifications and know quite a bit about it, and some of you will work on some completely different things. So there's no ideal solution to this problem, but I wrote some notes which are already available on the website for the school. So in the notes, it covers the stuff that we'll discuss in the lectures, and it has some additional material and some additional explanations of things that I might not have time for in the lectures. So you might want to have a look at that if you want to have some more background or some more insight. Okay. All right. So part one, as I said, is just going to be heterotic compactifications. We're just going to talk about the classic story of string compactifications of the heterotic string. Okay, so like any superstring theory, of course, the heterotic string lives in 10 space-time dimensions, and it has n equals 1 supersymmetry, and it has the following bosonic fields. It has a metric. There's an antisymmetric tensor field, usually called the B field. It has a dilaton, and then it has a gauge field. And then, of course, there are some fermions. There's the gravitino, there will be a dilatino, and there will be a gaugino. Okay? So this theory in 10 dimensions, well, of course, there are also all the massive modes, but we're just going to effectively look at the massless modes, the low-energy supergravity theory. So this theory, of course, is going to have lots of symmetry. For starters, it has Poincare symmetry in 10 dimensions. In fact, as I said, it has n equals 1 supersymmetry, so it has 10-dimensional super Poincare invariance. And then this gauge field here, it comes in two flavors. For consistency, it's either SO32, actually more precisely spin 32 mod Z2, or an EA times EA gauge symmetry. Okay, so that's very nice, but it's a lot of symmetry. And perhaps we want to discuss compactifications which are more realistic or which have interesting field theories as limits. And so in order to do that, we're going to have to break all the symmetry to something more smaller and something more manageable. Okay? And the way we're going to break it, we're just going to use the standard Kaluza-Klein ansatz. We take our 10-dimensional space-time, and we will take it to be of a direct product form, 4-dimensional Minkowski space times some internal manifold. Okay? Of course, there are various variations on this that you can consider. Okay, you can consider compactifications to 8, 7, 6, 5, 4, 3, 2, etc. dimensions. I'm going to discuss mostly about string compactifications to 4 dimensions, and you can make some adjustments if you wish as we go along. Okay, so then the story of Kaluza-Klein compactification, it's this button, is, okay, so at short distances we recover our 10-dimensional Lorentz invariant, but at long distances I don't know if you can actually see this dot, I can hardly see it. But at long distances, distances which are large compared to the typical size of x6, we recover an effective 4-dimensional field theory. And we want to understand what kind of effective 4-dimensional field theory you can get by doing this type of compactification. Okay, so what are the possibilities that, what are the possible manifolds that we can take for x6? Well, the simplest possibility is just the standard, it's just a simple generalization of the standard Kaluza-Klein ansatz. So of course the original Kaluza-Klein ansatz took a 5-dimensional space-time, a 5-dimensional metric, and then we compactified it to 4 dimensions on a circle. Okay? So why don't we try something like that here? Now we have a compactification from 10 dimensions down to 4 dimensions. Now we just take 6 circles. In other words, we take a T6. All right? This is often referred to as a Narain compactification. The reason for that being that there is an elegant formulation of such compactifications, which started by Narain, which is based on the even self-dual momentum lattice of signature gamma 22 6. And okay, so this parameterizes the internal momenta, left and right moving momenta of the string. And the 4-dimensional effective theory is parameterized by this moduli space. This is just a moduli space of these of a lattice of this type. So it's this type of coset form. It's O22 mod O22 mod O6, and then there's some additional discrete symmetries that you have to mod out by. Okay, and the only thing that I wanted to remember about this is that it's not this particular form, but the fact that this so this is the moduli space describing deformations of the metric, of the B field, and of the gauge field along the internal space. Okay, so the metric, the B field, and the gauge field, they have some kind of profile along the T6. And you can vary this profile, and if you just take the standard setup, the space of profiles is parameterized by this coset space. Okay. Now, for our purposes, this is okay. So it's a very beautiful story. There are lots of nice things that you can say about this story, about this type of compactification. All right. Heterotic string is n equals 1 supersymmetry in 10 dimensions. That means it has 32 supercharges. If you do a straight reduction along a flat space down to 4 dimensions, 32 supercharges, that's n equals 4 supersymmetry in 4 dimensions. Okay, that's a lot of supersymmetry. All right. For example, I couldn't possibly get a chiral theory if I tried to break n equals 4 supersymmetry in 4 dimensions. For that, you can have at most n equals 1 supersymmetry. Okay, so this is a very nice story, but it's very restrictive, and so we want to relax that a little bit. We want to consider compactifications which have a bit less symmetry, which are a bit more general, and we're going to discuss compactifications which have at least n equals 1 supersymmetry in 4 dimensions. Of course, the techniques that I'll discuss, they will also apply as special cases to n equals 2 and n equals 4, but they will assume at least n equals 1 supersymmetry in 4 dimensions. Okay, so if you want to preserve some supersymmetry, well, you have to start with the 10-dimensional supersymmetry variations and try to find some transformations that are not broken. Okay. So, how do we find those unbroken transformations? So we just start with the standard supersymmetry variations of the heterotic string in 10 dimensions. So I've written here the variation for the gravitino, for the gaugino, and for the dilatino. And these are completely standard results from the supergravity literature. H here is dB. It's the exterior derivative of this 2-index tensor field. What else do I want to say about this? Yeah, so epsilon here is a 10-dimensional Majorana-Weil spinor, which parameterizes the 10-dimensional n equals 1 supersymmetry transformation. And of course, these are the transformations for the fermions. They're also transformations for the bosons of the form variation of bosons proportional to a fermion. Okay. Now, I do want to preserve some symmetry, so we want to have at least n equals 1 supersymmetry and Poincare invariance in 4 dimensions. So that we do want to impose. So if you want to impose that, then first of all the Fermi fields are going to have to vanish, because if any of the Fermi fields have a non-zero expectation value, then you will be breaking that 4-dimensional Poincare invariance. Okay, so that's essentially why I didn't write the transformations for the bosons, because the transformation of the bosons proportional to a fermion, but the fermions have 0 expectation value, so I don't need to worry about those. On the other hand, the variations for the fermions, there we go. They're proportional to some boson times epsilon. And the bosonic fields may have some non-trivial profile along the internal space. And nevertheless, as long as this equation, as long as delta psi vanishes, you will still preserve a supersymmetry transformation. Okay. So we want to find non-trivial solutions to these equations. We want to find non-trivial solutions to these equations where delta psi is 0, delta lambda is 0, and delta chi is equal to 0. Okay. If you found a non-trivial solution, that's non-trivial solution for epsilon, and h and f and phi, then you found some supersymmetry transformation which is unbroken by the compactification. Okay. Okay. Now we're going to make some further simplifications. We want to assume that this tensor field H vanishes, and similarly that phi is constant. Okay. There's a slightly more general story. When H is non-constant, it turns out that this particular ansatz is not sufficiently general to deal with that situation. It leads to the study of warped compactifications. It's significantly more complicated that I'm not going to go into it here. We're just going to describe the classic story. So the classic story is that H vanishes and phi is constant. And then if we look at all these equations, so we already said Fermi fields vanish, H is 0, phi is constant, so this is all satisfied. Over here, we get delta lambda equals fmn contracted with gamma mn. Gamma mn is just the antisymmetric combination of gamma m and gamma n, gamma matrices. Okay. So we want that to vanish. Okay, so that's this equation over here. And if we look at the first equation here, well, H vanishes, so we're only going to get this part here. So the covariant derivative of this spinor epsilon should vanish. Covariant derivative with respect to the Riemannian metric. Okay, so these are the equations that we want to study. And we're going to study them separately. So we're first going to study this equation in some detail. And then eventually, so for now, if you wish, you can think of f as being 0. And eventually we will get back to try and find non-trivial solutions to this equation. But for now, we just focus on this equation. Okay. Okay, so as I said before, so the spinor epsilon lives in a 10-dimensional Majorana-Weil representation, which is 16-dimensional, and has a real structure. Our Kaluza-Klein ansatz is of this form. A 10-dimensional space is Minkowski space times internal space x6. Okay. So now we want to decompose the spinors to be compatible with this structure. In other words, we want to decompose spinors under the SO13 times SO6 subgroup of SO1,9. Okay. So the way that works is follows. The 16 of SO1,9, it splits up under SO1,3 times SO6 into a chiral representation, 2 of SO1,3 times a chiral representation, which is 4-dimensional SO6. Again, these are both the spinor representations of SO1,3 and SO6. And then these are the complex conjugates. So this is the emission conjugate of that one, and this is the conjugate of that one. So I've written here in terms of the spinor. So the epsilon 4 plus sits in the 2 here, and the epsilon 6 plus sits in the 4 here, and these are their conjugates. Okay. Now the supersymmetry transformation we'll be looking at will just be constant in the Minkowski space directions. The non-trivial, the interesting part comes from this. So the epsilon 6 plus and epsilon 6 minus are going to have some non-trivial profile over the internal space. Okay. The covariant derivative of epsilon is only really interesting if you look at the covariant derivative along the internal directions. So I used capital M here for 10-dimensional indices and little m here for 6-dimensional indices and x6. So just taking that and factoring it, tells you that this internal spinor has to be covariantly constant, both for epsilon 6 plus and epsilon 6 minus. Well, the conjugates of each other, so it's not a big deal. Okay, so in order to preserve some supersymmetry, in order to have some unbroken supersymmetry transformation, this manifold X6 must admit a covariantly constant spinor. All right? Now, existence of a covariantly constant spinor imposes, in general, in this case also, in general, it tends to impose very strong conditions, very strong geometric conditions on your manifold. And so we now want to discuss some of the structure that's implied by this requirement of having a covariantly constant spinor. Okay. So the first thing, you can just look at the norm. Epsilon 6 star epsilon 6. Sorry, I couldn't do a dagger in my equation editor, so it's just epsilon star instead of epsilon dagger. But basically, by Leibniz rule, that norm vanishes. So that means that you can just rescale it and set it equal to 1. Okay, so we'll assume that. But then there are other interesting bilinears that you could look at. So there's this bilinear, which is epsilon 6 plus dagger, gamma mn epsilon 6 plus. And gamma mn is the basic Lorentz generator, is the basic SOD generator. Okay. With the I in here, this better be a real tensor. And if you do some calculations with spinor calculus, then you find that if you take jmn, jnp, and sum over n, of course, Einstein's summation convention, that it's equal to minus delta pm. Or in other words, in symbolic notation, j squared is minus 1. Okay? So we have a real tensor which squares to minus 1. So an endomorphism of the tangent bundle which squares to minus 1. And that should remind you a little bit of complex structures, right? In complex structures you have I, and I squared is minus 1. Or if you want to do this in real notation, you have a real 2-plane, and you have this 2x2 tensor, which you can write as 0, 1, minus 1, 0, right? It squares to minus 1. That's your complex structure. So it's very reminiscent of a complex structure, but it's not actually necessarily implies what we usually mean by complex structures, namely that you can write local holomorphic coordinate systems. So having a tensor which squares to minus 1 is a necessary condition. It turns out that it's not quite a sufficient condition in order to write local holomorphic coordinate systems. So that's why this is called an almost complex structure. It's almost complex, yeah. So it's not quite a complex structure, it's an almost complex structure. Okay? So if you want the additional requirement that you actually have a complex manifold, that means you can actually write local holomorphic coordinate systems, then there's an extra condition on this tensor. And this condition, okay, so there's an integrability condition. It's the vanishing of the Nijenhuis tensor. So there's this Nijenhuis tensor, n with 3 indices, which is basically j, covariant derivative j, etc., with various permutations of the indices and of the signs here. Okay, just a word on pronunciation. So I often hear this pronounced as Nijenhuis or something like that. Okay, so I think Albert Nijenhuis was a Dutch mathematician, and so it's called Nijenhuis. Okay, so god-awful looking tensor. What the hell is that? Well, maybe it just gives you a little bit of intuition where this comes from. If you have such a tensor which squares to minus 1, okay, by taking complex linear combinations of eigenvectors, you can project things on the plus I eigenspace or on the minus I eigenspace of this tensor. Okay. And now the basic problem is that if you have two tangent vectors which are in the plus I eigenspace, two complexified tangent vectors which are in the plus I eigenspace, and you want to think of this somehow as being associated to a holomorphic coordinate system, then the Lie bracket of those two vector fields has to vanish. Okay? And that's not implied by just having an almost complex structure. So the basic problem is that if I take a complexified tangent vector in the plus I eigenspace and then take another one, and then I take the Lie bracket, I should get another plus I eigenvector. And that's not necessarily the case. So now by projecting on the minus I eigenspace, I get a tensor. And by rewriting it a little bit, that's essentially this tensor here. Okay, so use some identities to show that that's that tensor. So it's a necessary condition that this tensor vanishes. It's in fact also a sufficient condition. That's a little more complicated, but it's a well-known theorem of Nierland and Nierenberg. if this tensor vanishes, then you can also construct holomorphic coordinate systems. Okay, now, so in general, almost complex structure does not imply complex structure. There are explicit counterexamples to that. But in our case, we have a bit more structure. So remember that the covariant derivative of our spinor vanishes. And of course, this is just a bilinear. So the covariant derivative of this thing also vanishes. Okay. Now, if you go back to the Nijenhuis tensor, you see that all these things are proportional to a covariant derivative, and therefore they all vanish. Okay. So in the situation at hand, where we have a covariantly constant spinor, this tensor actually does vanish. This complex structure is integrable, and therefore X6 actually is a complex manifold. Okay? Now, if you're on a complex manifold, and we will be in a complex manifold for quite a while, it's often convenient to use complex coordinates rather than real coordinates. A lot of the symmetries and properties will be a lot more self-evident when you use complex coordinates. So I'm typically going to use coordinates. So Z will typically denote Z upper J will typically denote a complex coordinate where the indices go from 1 to 3. So I need 3 complex coordinates to describe X6. So Z1 is like X1 plus IX2. Z2 is like X3 plus IX4, etc. Okay. And the other thing I'm going to do is instead of the real tangent bundle, I will typically want the holomorphic tangent bundle. So it's locally spanned by d by dCj. Okay. And sometimes people use special notation for a holomorphic tangent bundle in order to distinguish it from the real tangent bundle. I don't want to do that. It's going to get a lot of notation. And the convention I'll use is that if X is a real manifold, T of X will be the real tangent bundle, and if X is a complex manifold, we use T of X to denote the complex tangent bundle, spanned by d by dCj. Should be no confusion, as long as you're sure whether you're dealing with a real manifold or a complex manifold. Okay? Similarly, the holomorphic cotangent bundle is T star of X, which is spanned by the codifferentials, by the covectors, excuse me. And if I want the anti-holomorphic versions of these, I will just put a bar on them. Okay, a little bit more algebra. This one's actually really easy given the identities on the previous transparency. You also find that the complex structure is compatible with the metric in this sense. And in other words, that the metric is a Hermitian metric. And since we're now going to typically work in complex coordinates, you can put this tensor J in the standard form. So remember, my J and K are holomorphic indices. And J bar and K bar are going to be the anti-holomorphic versions of these indices for Z1, Z2, and Z3. So I can now put this tensor then in the standard form, where it acts as plus I on holomorphic tangent vectors and minus I on anti-holomorphic tangent vectors. Okay. And if you now just plug this in, this equation, you'll see that the IJ components and the I bar J bar components of the metric just vanish. And the only non-zero components are the IJ bar component and the I bar J component. Okay. So if you wish, this is a tensor of type 1, 1, where 1, 1 means it has one holomorphic and one anti-holomorphic index. And the 2, 0 and the 0, 2 components, that is the 2 holomorphic and 2 anti-holomorphic indices, those pieces both have to vanish. Okay. Now, if you're given such a 1, 1 a tensor, you can construct an associated 2 form. In this case, it's called the Kähler form. So we just take Gij bar, DCI width to J bar. Okay. The covariant derivative for J was 0, so this thing is actually going to be closed. And so a Kähler manifold is so a complex manifold which has such an associated 2 form which is closed is called a Kähler manifold. Now, this definition probably doesn't seem like much, but if you study Kähler manifolds a bit more, they turn out to have a lot of very nice properties. They're very symmetric. I saw this morning, I already saw Kähler potentials being written, so you already know to some extent about Kähler manifolds for sure. As we go on, we'll just see a few more properties of Kähler manifolds, some of these nice properties of Kähler manifolds, which are not evident from this definition, but which are nevertheless true. Okay, further consequences. Well, I could have done this one at the beginning, I suppose. So if epsilon 6 is covariantly constant, just by taking the anti-commutator, well, the anti-commutator is just going to give you the curvature. Okay. So you find that the curvature contracted in this combination with gamma pq acting on epsilon must vanish. And now again, a little manipulation. Basically what you do is you contract it with another gamma matrix, gamma n, and use some gamma matrix identities and the first Bianchi identity, and you end up showing that you end up with the Ricci curvature, which therefore has to vanish. Okay. So our X6, if it has a covariantly constant spinor, not only is it the Kähler manifold, it's in fact the Ricci flat Kähler manifold. Okay. Now on any Kähler manifold, again, so this Ricci tensor turns out to be, on a Kähler manifold, turns out to be of type 1,1. It has no 2,0 or 0,2 components. And so just like we did for the metric, we had this 1,1 tensor, we constructed associated 2 form, the Kähler form. So we can use Rij bar to construct an associated 2 form, which is often called the Ricci form. Okay. And by the second Bianchi identity, this thing will be closed. Therefore, it defines a cohomology class. And this cohomology class is what we often call the first Chern class. So the first Chern class is usually defined in a slightly different way, but it turns out to be equivalent to this. Okay. So this is a first Chern class. So it's a de Rham cohomology class. So it's a topological quantity. And now if you have a Ricci flat Kähler manifold, Rij bar vanishes, and therefore the first Chern class is a 0 cohomology class. Okay. So we have a topological condition. Well, we have a condition that we have Kähler manifold and Ricci flatness. That in particular implies this topological condition that the first Chern class as a cohomology class vanishes. Now it turns out that just having these two conditions, namely Kähler and this topological condition that the first Chern class vanishes, it turns out that that's actually sufficient to show that there exists a solution to this equation. Okay. So that ends up being a famous theorem, which I'll discuss in a few slides. But before we do that, we have to, we can gain some more insight into this problem by looking at this whole setup from the point of view of holonomies. So let's step back a little and discuss a little bit about holonomies on a manifold. Okay. So how did that story work? Okay, well, just give me a general manifold M. Okay, and let's say it is d-dimensional. And let's consider a loop which is based at some point P by manifold M. So this loop is parameterized as a curve called gamma T. Okay. And now, if you give me a tangent vector, okay, then I can parallel transport it around the loop. So what does that mean? Well, I make, so I consider a vector field V of t along the loop, okay? And this vector field has to be, its derivative in the tangent direction to the loop has to vanish. So those are the equations that I want to study for parallel transport. It's an ordinary differential equation, so I specify the initial conditions, which is that V0 is just V, and I parameterize the loop such that after 2 pi, I come back to myself. Okay, so you solve this equation with this initial condition, you go around the loop, and you find some other vector, which we will call V prime. And now I'm assuming here that I've used the Riemannian connection, like Jupiter connection. In that case, if you go around this loop, then V prime is related to V by an SOD transformation. SOD, again, D being the dimension of our manifold. Okay? Now, okay, this is if you take one loop. You can take multiple loops and just compose them with each other. And then you get a group structure on these matrices R. And if I consider all possible loops, this will generate a subgroup of SOD, which is called the holonomy group of my manifold. Well, my manifold plus the metric, really. Plus the Riemannian metric. And in general, if you have no extra structure, if you just have a Riemannian manifold, then in general you will generate all of SOD in this way. So the holonomy group would be all of SOD. However, if you have some extra structure, then you'll typically end up with a subgroup of SOD. Okay? And that's the situation that we're going to have here. We have extra structure. We have, in fact, this very strong condition of having a covariantly constant spinor. So we will effectively end up with having a subgroup of SOD. Furthermore, there's a very close connection with the curvature. So if I take a very, very small loop, infinitesimal loop with an infinitesimal area element delta AMN, okay, you can do a local calculation of this holonomy around that infinitesimal loop, and it's basically it's delta PQ plus this contraction of the area element with the curvature. So this is an SOD matrix. So this is an antisymmetric matrix, and delta plus that is to first order is an orthogonal matrix. This is an infinitesimal orthogonal transformation if you go around the infinitesimal loop. Okay. But the point being that we have the curvature appearing here, right? So this holonomy group element can be expressed in terms of the curvature, and by building up your big loop in terms of small loops, see that let me put it this way. So you generate all of SOD if there's no extra structure, but if you do have some extra structure, then there will also be some extra restrictions on the curvature. Okay, so this is for tangent vectors, but you can really transport anything around the loop. Well, anything meaning any other tensor, or even a spinor, which is not a tensor. You can also transport spinors around the loop. So that's what we're going to do now. So because we had this covariantly constant spinor, so we want to see what kind of restrictions we get on the holonomy. Okay, so the first thing I want to use to simplify our life is this classic identity between Lie groups. So spin 6 being the double cover of SO6, right, is actually isomorphic to SU4. And the spinor representation, the 4 of spin 6, the positive correlated spinor representation, is actually the fundamental representation 4 of SU4. Yeah. The anti-Cairo version of this is the 4 bars, the anti-fundamental of SU4. Okay, so now we want to take our epsilon 6, and we assume it's covariantly constant, and we want to transport it around the loop and see what happens to it. And the basic story is that nothing happens to it. So why is that? Well, if there exists a globally defined covariantly constant spinor, okay, you can just take that, restrict it to the loop, all right, and then contract it with gamma dot. So in other words, differentiate in the tangent direction. And because this thing was covariantly constant, that gives you a solution to this ODE. And ODEs, of course, you have existence and uniqueness. So once you specify the initial value, you specify the final value. And because this is globally defined, you just end up coming back to yourself. Right? So nothing happens, really. Okay, but what does that mean now? That means that the holonomy group, it can't be all of SO6. It has to, or spin 6 if you wish, because we're working with spinors now. It has to be some subgroup of SU4 that preserves epsilon 6. Okay? Because it has to come back to itself, and a general SU4 holonomy would not bring you back to yourself. So now we just use, first of all, we just use a standard, we just use some SU4 transformation to put epsilon 6 in the standard form, where, okay, so it's an element of the 4-dimensional vector space. So I just take the first 3 components to vanish and the last component to be non-vanishing. Okay, you can always do that if it's non-vanishing. And so what's the subgroup of SU4 that preserves this? Well, it's of course it's SU3, the thing that acts, it's the subgroup that acts on the first 3 indices here. Right? So the stabilizer, notice the subgroup that fixes epsilon 6 plus is SU3. So what we've just seen from this discussion is that having a covariantly constant spinor is the same as saying that X6 has to have SU3 holonomy. In general, if you want one covariantly constant spinor, it has to be exactly SU3 holonomy. If you reduce it further to SU2 or something like that, you can get additional covariantly constant spinors. Okay, so now let's think about this a little bit more. So let's try to connect it with some of the other things that we said before about Kähler manifolds and Ricci tensors and so on. Okay, now a Kähler manifold actually has, turns out to have U3 holonomy. So a Kähler manifold also has special holonomy. It's not a generic SOD holonomy. This extra structure, it has this Kähler form, J, which is covariantly constant. Okay? And if you now parallel transport the Kähler form around the loop, it also has to come back to itself. So the subgroup of SO6 that preserves the Kähler form is U3. Okay. Now, U3 is essentially reducible. It has an SU3 part and it has a U1 part. Okay. And the U1 part of the U3, that's just the determinant. 3 by 3 complex matrix, which is unitary. The U1 part is just the determinant. All right? Okay, geometrically, so now if we want to discuss U3 holonomy, how can we see just, so now we want to have some geometric quantity which transforms just under the U1 part and not under the SU3 part. Okay? And what is that? Well, cotangent vectors actually transform like so DZI, things you had before, they transform in the fundamental 3 of U3. So if you take wedge 3 cotangent of X, so forms that locally look like DZ1, wedge DZ2, wedge DZ3, okay? So they transform precisely, they transform as the determinant, so they transform precisely under the U1 part of this holonomy. Okay? So if we just want to look at the U1 part of this holonomy, well, it's generated by parallel transporting 3,0 forms around the loop. 3,0 forms come back up into a phase, in fact, a complex phase, and that phase is this phase. Okay? Now that means, well, I keep pressing the wrong button. Okay, what does that mean? That means that if we have SU3 holonomy, which we get if we have a covariantly constant spinner, this U1 part of the holonomy has to be trivial, okay? But U1 is just the holonomy of this line bundle, so this line bundle has to be a trivial line bundle. Okay? Another way to see this, okay, so there are multiple ways to see this. We can actually write down a global section of this line bundle. We can actually write down a global section of this line bundle, which is nowhere vanishing, and therefore it trivializes the line bundle. What is it? Well, I take epsilon 6, and now I take another bilinear. So in between, I wedge it with gamma ijk, which is, again, ij and k are holomorphic indices and totally anti-symmetrized. So this is actually a 3-0 form, right? Wedge it with dz1, wedge dz2, wedge dz3. Remember that epsilon 6, star epsilon 6, the norm of this thing was 1 everywhere after always scaling, so it's nowhere vanishing. It is a line bundle, so this whole thing is also nowhere vanishing. It's often called a holomorphic volume form by analogy with the volume form on the real manifold, which is a section of the top exterior power of the cotangent bundle of the real manifold. And as I said, it's nowhere vanishing, so this explicitly trivializes this line bundle. Wedge 3 of cotangent of X. So that's a trivial line bundle. And in fact, the converse is also true. So you can actually compute the curvature of this line bundle, all right? And I won't do it here, but if you compute the curvature of this line bundle, it's exactly the Ricci form that we encountered previously. Okay? So so if we're in the situation that we had previously, where we already saw that we have a Kähler manifold which is Ricci flat, which is implied by a covariantly constant spinner, well, that means that the curvature of this line bundle is identically 0, and therefore it's a trivial line bundle. Well, if the fundamental group of your manifold vanishes, otherwise you have a slight additional argument, but that's the basic idea. Okay, but that means that curvature vanishes means that 3,0 forms are parallel. And that 3,0 form is transformed into this U1 holonomy. So this U1 holonomy is trivial, therefore we have SU3 holonomy, and therefore we have a covariantly constant spinner. So the converse is also true. Not only does SU3 holonomy or covariantly constant spinner imply Ricci flat and Kähler, but conversely Ricci flat and Kähler implies SU3 holonomy and covariantly constant spinner. All right. Okay, so now that's about as far as you can go without invoking some difficult theorems. So At this point, we've reduced the problem of finding an unbroken supersymmetry. We've reduced the problem to finding a covariantly constant spinor, and we said that's equivalent to finding a Ritchie-flat and Kähler manifold. But Ritchie-flat metrics are really hard. It's very hard to write down explicit Ritchie-flat metric on a Kähler manifold. And in fact, there are basically no non-trivial solutions of such Ritchie-flat metrics known. So what are you going to do? Okay, well, let's first make a brief definition. So we define a Calabi-Yau manifold to be a Kähler manifold whose first Chern class vanishes. Okay? So, as we saw before, in order to solve this BPS equation, this covariantly constant spinor equation, it's a necessary condition that the Kähler manifold vanishes and that this topological condition, the first Chern class, vanishes. Okay? Right, Ritchie-flat and Kähler, the Ritchie-flat, the C1 of X is basically the cohomology class that you constructed from the Ritchie tensor. So Ritchie-flat certainly implies that C1 is 0. Now, the converse is not at all obvious, but it's true. So what do I mean by the converse? The converse, I mean Kähler plus vanishing first Chern class. So vanishing first Chern class is a topological condition. Vanishing of the Ritchie tensor looks like a differential geometric condition, so it looks like a much stronger condition. One implies the other, but why would the other imply this one? And nevertheless, it's true. So it's a famous conjecture due to Calabi, which was then proven by Yau, the famous theorem. So it says precisely that a compact Kähler manifold with a vanishing first Chern class emits a Ritchie-flat metric. Moreover, this metric is uniquely determined by the complex structure and by the Kähler class. Okay? So this simplifies life enormously. Finding an explicit Ritchie-flat metric and finding an explicit metric and showing that it's Ritchie-flat is an impossible task. But we don't need to. You merely need to check that the manifold is Kähler and that the first Chern class vanishes, that we have this topological condition. And then Yau's theorem would tell you that for any complex structure in Kähler class, there exists a unique Ritchie-flat metric with that Kähler class and that complex structure. And so you only need to check the Kählerness and you need to check this topological condition. And then you know it exists. I still won't be able to actually write down the metric. That's too hard to do. But there's an existence theorem which will tell you that it exists. Okay, so summary of our long discussion can be just summarized in the following bullet points. We've shown that the following conditions on our 6-manifold X are all equivalent. X emits a covariantly constant spinor, this equation, so that's what we wanted in order to find an unbroken supersymmetry transformation. We've seen that it's equivalent to the manifold having Escher-3 holonomy. Then we further saw that that's equivalent to the manifold being Kähler and having a Ritchie-flat metric. And then finally, and perhaps most surprisingly, that's equivalent to X being a Calabi-Yau manifold, meaning it is Kähler, and it satisfies this topological condition of having a vanishing first Chern class. So obviously, we're not going to really use the first three very much if we want to construct explicit examples. If you want to construct explicit examples, you just want to use this last version of the statement. All right, so let's discuss some well-known canonical examples, which you've probably seen at some point, if you looked at any of this before. So everybody's favorite example of a Kähler manifold is just a complex projective space. So we just take n+1 complex coordinates, 0 up to Cn. We excise the origin, so we don't want them all to be simultaneously 0. And then we identify C0 up to Cn with lambda times C0 up to Cn, where lambda is some non-zero complex number. Yeah? So we mod out by that equivalence relation. That gives you a space. In fact, it's a compact space, and this is n-dimensional, and it's a complex projective space. It's not Ritchie-flat. In fact, the first example would just be CP1. That's a two-sphere, and a Ritchie-flat metric on a two-sphere would just be a flat metric on a two-sphere. Of course, you can't put a flat metric on a two-sphere. Okay? So CP1 is certainly not Ritchie-flat, and the same is true for the other CPNs. So we have a Kähler manifold, but we don't want just a Kähler manifold. We want a Ritchie-flat Kähler manifold. We want a Kähler manifold which has a vanishing first Chern class. This isn't it. But holomorphic submanifolds of a complex projective space are also Kähler. Basically, you pull back the Kähler form, it will still be closed, it will still be positive, so that will still work. And how do you find holomorphic submanifolds of complex projective space? Well, you just write down a complex equation. Just write down some degree n polynomial that will define a holomorphic submanifold of complex projective space for you. And by adjusting the degree of the polynomials, you can ensure that the first Chern class vanishes. Okay? So that won't be true for any degree of your polynomial. If you choose the degree just right, the first Chern class of this holomorphic submanifold will vanish. Holomorphic submanifolds, incidentally, are usually that are defined in this way, are usually called for polynomial equations, are usually called algebraic varieties. Okay, so if you just consider CPN, simplest case, it turns out that you want an equation of degree n plus 1. Okay? So that's, there's a simple calculation you can do, which then tells you that the first Chern class vanishes. You can find the notes if you want. Okay, so that leads us to perhaps the most famous Calabi-Yau threefold of all. We just take CP4, okay, and that's 4 complex dimensions. You want a threefold, so you want to impose one complex equation to get a threefold, okay, and we want to take the degree of this to be 4 plus 1, which is 5. Okay? So you just write down a generic degree 5 polynomial. I've written a special one here, the Fermat hypersurface, but you could consider deformations of this. Okay? And this is called the quintic for obvious reasons. It's of degree 5. Okay? And this is probably the most famous example of a Calabi-Yau threefold. Again, if we don't know much about the Ritchie-flat metric, certainly can't write it down explicitly in closed form, although we can approximate it. But by Yau's theorem, we know that there exists such a metric on the quintic. Okay? This works in any dimension, so just quickly do some other examples, right? So if you do this in CP3, take a hypersurface in degree 3, of degree 4 in CP3, that gives you a 4 manifold, or complex surface, which is Calabi-Yau. That's the famous K3 surface, which you might have heard of. And of course, if you take an equation of degree 3 in CP2, you have to get a Ritchie-flat Riemann surface, so that's got to be the 2 torus. Of course, that's the 2 torus. Elliptic curve, it's also called. Okay, here's another famous example of a Calabi-Yau threefold. It's called the Chien-Yau manifold. This time we're going to take 2 factors of CP3. And so I have 2 sets of coordinates, C0 up to C3, W0 up to W3. And I impose the following 3 equations. It's degree 3 in these coordinates, degree 3 in the W's, and it's degree 1, 1 in the last final equation. You may wonder why it's famous. Well, this thing has Euler character 18, and it actually emits a freely acting Z3 symmetry, which you can mod out by. And if you do that, you find a manifold which has Euler character 6. And okay, so the fact that this thing is Euler character 6 has some special significance. I'll probably comment on later or perhaps next time. Okay, so now I want to discuss some more general properties of Calabi-Yau manifolds, the general structure of Calabi-Yau, the geometry of Calabi-Yau manifolds. And I think this will probably also be useful for Professor Oguri's lectures. So I want to pay attention for that reason as well. So of course, these are going to be geometric properties of the manifold, but they're also going to tell you some effective properties about the effective 4-dimensional theory. That's obtained by compactifying a 10-dimensional heterotic string under Calabi-Yau. And okay, so the basic outline, the basic structure of what I'm going to do is I'm going to very quickly state some properties about differentiable manifolds that I essentially assume you've seen before, and just repeat them for convenience, and then I'll state the complex analogs of them that you might not have seen before. Okay, so the main thing that I want to discuss is the Hodge decomposition and the issue of harmonic forms and so on. Okay, so let's think again. So let's step back just for a second and think about differentiable manifolds. So on on a general differential manifold, you can define differential forms. And differential forms fit in a complex. That is, I can write it as a sequence like this. So there's a sequence of degree 0 forms, degree 1 forms, up to degree d forms. So d is the dimension of my manifold. And this map here, which takes you from degree k forms to degree k plus 1 forms, that's the exterior derivative. Okay, so there's a natural derivative acting on differential forms, which is the exterior derivative. And d squared is 0, so the composition of any of these two maps is 0. That's why it's called a complex. Okay? Whenever you're in a situation like this, when you're in a complex, you have a sequence like this with a sequence of maps whose composition vanishes, you can define cohomology. In this case, it's called the round cohomology of differential forms. So you just take the closed k forms and you mod out by the exact k forms. In other words, you impose an equivalence relation. Two closed k forms are said to be equivalent if they differ by an exact k form. And closed, I remind you, means that it's annihilated by d. It's in the kernel of this exterior derivative d. And exact means that it's in the image of the exterior derivative d. Okay? Furthermore, there's a natural metric. Given a metric on a manifold, you can define a natural metric on the space of differential forms. L2 inner product on the space of differential forms. You just take alpha, wedge it with the star of beta. This is the Hodge star operator. And so it's basically contraction of the form of the epsilon tensor and then lower some indices with the metric. Right? And once you have an inner product on differential forms, I can define an adjoint of any operator. In particular, I can define an adjoint of the exterior derivative with respect to that inner product. Okay, so that adjoint is denoted by d upper star. And we can define a Laplacian, which is d star plus d star d. Okay? So at the leading order, this will look something like gmn, d by dxm, d by dxn, plus various corrections. So the leading order looks like a Laplace operator. Okay, and it's a natural Laplace, so all these things act naturally on differential forms. So it's a Laplace operator for differential forms. Okay, so then the Hodge decomposition is the following statement. Given a general k form, I can decompose it into 3 pieces. And in fact, this decomposition is orthogonal with respect to this inner product that I just showed you. What are these 3 pieces? Well, there's a harmonic piece. So there's a piece that's annihilated by the Laplacian. And then there's an exact piece, and then there's a co-exact piece. Okay? And all these things are orthogonal. Furthermore, it follows from this. Okay, so this is the basic statement, and there's now a lot of things that follow from that. Particularly, it follows from this that if you take a closed form, then and you do the decomposition, you're only going to get a harmonic piece and you're going to get an exact piece. Okay? And now if I'm interested in closed forms modulo exact forms, okay, I can effectively get rid of this piece. I can always gauge that away. And so what you find is that every cohomology class emits a unique harmonic representative, which is this alpha h here. Okay? So that's the basic statement. It's a very important statement. And it's a little weird in a way, if you think about it, because the notion of harmonic form clearly depends on the metric. Okay? Cohomology doesn't care about the metric at all. Indeed, if you vary the metric, okay, so you change the metric on your manifold, cohomology of your manifold is not going to change, the round cohomology doesn't change. The harmonic form does change because it depends on the metric, but nevertheless, for every cohomology, in every cohomology class, there exists a unique harmonic representative. Yeah? I couldn't hardly hear you, I'm sorry.
In 2 dimensions, could we have 3 perpendicular directions for the forms? So let's say n is 2-dimensional.
Yeah.
Could this work perfectly as well?
Does what work perfectly? You mean the decomposition?
Yes.
Well, I think so. Just the k 0, 1, and 2. Yes?
Martijn, what was the question?
I think I'm not sure why it's asking, but if this decomposition.
What d star makes
Oh, I'm sorry, that's a typo. That's a typo. Yeah, I'm sorry. So this is a k minus 1, this is supposed, right, so, okay, thank you. That's a typo. So the adjoint of D takes you from, so D takes you from k forms to k plus 1 forms, but the adjoint of D, if you just look at this formula, you see that it takes you from k forms to k minus 1 forms. Okay. So if you want this to be a k form, okay, you have to take this to be degree k plus 1 form. And if k equals 2, okay, you don't get this piece. Maybe that's what you were asking. Okay, that's a typo. Thank you. Okay. Okay, so that's the story for real manifolds. Now we're going to be dealing with complex manifolds, and so it's natural to deal with complex differential forms. And so we're going to have expressions dz and dz bar and so on. And in a complex manifold, it's useful to keep track of the number of holomorphic and the number of anti-holomorphic indices. Okay? So the forms, they come in a PQ type, where P denotes the number of holomorphic and Q denotes the number of anti-holomorphic indices. Okay? Similarly, the exterior derivative splits up into a del and a del bar part, where the del bar part acts, so it increases the number of anti-holomorphic indices by 1, and the del part increases the holomorphic indices by 1. Okay? And since d squared is 0, and by preservation of type, you also find that del bar squared is 0, del squared is 0. In fact, you also find that del bar plus del bar del is 0. Okay, now, anytime you see an operator such that its square vanishes, you can construct some kind of cohomology. So here we just take PQ forms, and so del bar only acts on the second index now. It increases the number of anti-holomorphic indices by 1 every time. And this is a complex because the composition of these two maps is del bar squared, which is 0. Okay? So then we define Dolbeau cohomology. The closed forms, that means the kernel of d bar modulo the exact forms, means the image of del bar. Okay, so this defines a cohomology group denoted by HPQ sub del bar. And we usually use capital H to denote this group as a vector space. If you want just the dimension of this as a vector space, we usually denote it by little HPQ. So the little HPQ is an invariance of your manifold X, which are called the Hodge numbers. Okay? So there's a little refined, so this is a little bit more refined in a way compared to Narain cohomology. Narain cohomology just had the degree of a form. Now we have the bidegree of a form. Okay? And again, you can write down a natural inner product on the space of complex differential forms and use that to define an adjoint. And then we can construct a Laplace operator, which is called the Dolbeau Laplacian, which is del bar, dagger plus del bar, dagger, del bar. Again, that's a Laplace type operator. And there's a Hodge decomposition for del bar. So any PQ form can be decomposed into a harmonic piece, harmonic with respect to this Dolbeau Laplacian, plus an exact piece plus a co-exact piece. And now, thankfully, I got the index right here. Okay? And again, from this it follows that every class in HPQ has a unique harmonic representative. Harmonic now being harmonic with respect to the Dolbeau Laplacian. Okay? Okay, so that's a story for complex manifolds, but we have a lot more. We have a Kähler manifold. And I told you before that on the Kähler manifold, we have a lot of additional relations, a lot of extra symmetry. It turns out that if you do a little calculation, you find that on a Kähler manifold, the D Laplacian is actually up to a factor of 2. It's actually the same as the Dolbeau Laplacian. Okay? So what does that mean? Well, first of all, it means that the harmonic forms of these two operators agree. It also means that the D Laplacian, it doesn't obviously preserve type. This one does obviously preserve type. So this one must therefore also preserve type if you're on a Kähler manifold. So it maps PQ forms to PQ forms. Okay, so the projection of a complex differential form, its PQ component commutes with this Laplacian operator. And so just by now decomposing everything into harmonic forms, you find that there's a decomposition of the real Narain cohomology into these Dolbeau cohomology groups, as long as the bidegree P and Q adds up to K. Okay. There are additional symmetries on the Kähler manifold. Okay, so we have a complex conjugation symmetry, which relates PQ to QP. The Hodge star isomorphism takes PQ to n minus P, n minus Q. Here, n is the complex dimension of my manifold. So if the real manifold is D, I take D to be 2n. Okay, so this takes PQ to n minus P, n minus Q. It's also true that if you're on a manifold with SUN holonomy, and if you look at the I0 Hodge numbers, then they always vanish unless I is equal to 0, I is equal to 1. This is a Weizenbuck identity to show that, which is in the notes if you want to see it. Okay, so now if you take all these symmetries and all these relations into account, you find that at the end of the day, if you look at all the Hodge numbers, there are only 2 independent Hodge numbers left. And we can take them to be H11 of x and H21 of x. Okay, so let's see that. So here's the Hodge diamond. Well, it's a diamond if you maybe rotate it by 45 degrees. Couldn't do that. Okay, so here you have them all, H00 to H03 up to H33. Okay. So H00 is obviously 1. H30, because there's a unique holomorphic 30 form, is also 1. We set these things are 0 by the Bloch-Weizenbuck identity. Okay, and then there's relations here which relate H12 to H21. There's Poincare duality which relates H11 to H22. Okay, so fill in all these symmetries and you're just left over with H11 and H21. Okay? Now, so there are only 2 degrees of freedom for a Calabi-Yau in the Hodge diamond, and they have a nice interpretation. So first of all, recall that by uniqueness of the Calabi-Yau metric, there's a unique Calabi-Yau metric if I fix the complex structure and if I fix the Kähler class. So that means now that the moduli of the metric are given by deforming the Kähler class and by deforming the complex structure. Okay? So now it turns out that H21 counts these complex structure deformations, and H11 counts the Kähler deformations. Okay? So for example, for a quintic threefold, so how do you deform the complex structure? Well, we had this degree 5 polynomial, and in fact I wrote a very special one. I wrote a Fermat quintic. You can just deform it to a generic degree 5 polynomial, and it turns out that such a generic degree 5 polynomial, if you do the count, it depends on 101 parameters. And now so is maybe a little strong, but nevertheless it's true that H21 of the quintic is precisely 101. Okay. Okay, the other thing you can do is not deform the complex structure, but deform the Kähler class. So how can we deform the Kähler class of a quintic? Well, remember that the quintic sits inside CP4. Okay, so the CP4 is a breathing mode. You can blow up the size of CP4, and I don't change the equation of the quintic by doing that, so the complex structure is still exactly the same. So that's a Kähler mode. Right? In fact, it's just a deformation of the Kähler metric which preserves type, right? Because it's just rescaling the Kähler metric by a factor of t. So that gives me one Kähler deformation, and H11 for the quintic is 1. Now, counting in this way is a little bit hazardous in general. It happens to work for the quintic, just counting. But in general, you find that if you consider some embedding in projective space, you find that there are some deformations of the metric which cannot be realized if you want to stay within that projective space. Yeah, so I don't have time to go into that. But it's still true in general that H21 counts complex structure deformations and H11 counts Kähler deformations. Now, given the time, okay, so I wanted to say maybe a few words. I wanted to say maybe a few words about why this counts complex structure deformations, why this counts Kähler deformations. I think I'm going to skip it. Basically, very briefly, right? Deform the Kähler class, you just need a cohomology class of degree 2, and the only cohomology class of degree 2 that you have is H11. And this one, how does that come about? Well, one way to see it, if you deform the complex structure, you're deforming the 3-0 form. And the first order of the 3-0 form goes into 2-1 forms. So these are the tangent vectors to the complex structure moduli space, and they're H21 of them. Okay, you can find some additional arguments in the notes if you wish. Okay, so the metric moduli space is this complex structure moduli space and the Kähler moduli space. And then we can add deformation of the B field. Again, the B field, so of course it has to satisfy the equation of motion when you deform it, which says that the internal wave function has to be harmonic. And they're precisely H2 XR harmonic 2 forms on a Calabi-Yau, and remember from the Hodge diamond, H22 in fact is H11. So we compare these scalar deformations with B-field deformations. In fact, we usually do this by combining the Kähler form with the B-field into a complexified Kähler form, J sub C, and then we just count deformations of this complexified Kähler form. And so the upshot is that adding the B-field deformations is basically has the effect of complexifying M Kähler. Okay, so that's more or less what I wanted to say about Calabi-Yau manifolds. Well, about general properties of Calabi-Yau manifolds. Now we're going to have to move on to bundles. So we've discussed the metric, and we just had a very quick discussion of the B-field. Okay, and but remember when we were looking for unbroken supersymmetry transformations, we had an additional equation which I told you about, which is that the variation of the K-geno, which is Fmn contracted with gamma mn acting on epsilon 6, this has to vanish. Okay? So we've discussed this condition, but now we've got to talk about this one. Okay, so how do we think about that? Well, the first thing to note is that on a Kähler manifold, you can rewrite this equation as saying that the 0,2 components, that is the components with the two anti-holomorphic indices of the curvature f have to vanish. And the other equation that you get from this is that Gij bar contracted with Fij bar has to vanish. This is sometimes called the Kähler trace. If you want to see this, well, one quick way to see it is that by putting in epsilon 6 transpose here, or an extra gamma matrix extra epsilon 6 transpose, and then using the fact that this gives the Kähler form and gives the holomorphic 3,0 form. All right. Now, so at any rate, so this is equivalent to that. So now let's discuss the meaning of these two equations. Okay. So first of all, I want to discuss the meaning of having the 0,2 component, the component, so everything that has two anti-holomorphic indices. That part of the curvature has to vanish. Okay, so we first look at the connection. You split up the connection to a 1, 0 and a 0, 1 part. Okay, and similarly then the covariant derivative has a 0, 1 and a 0, 1 and a 1, 0 part. So this is the 0, 1 part of the covariant derivative. And the commutator of the covariant derivative gives you the curvature. If you just look at the 0, 1 part, it gives you F02. But F02 vanishes. That's our condition. Okay. That means that A01 is pure gauge. Okay? And in particular, locally by a gauge transformation, you can just set this thing to 0. Okay, now now let's consider the gauge field in two patches and look at the overlap. Okay? So here we have a gauge field A01, here we have a gauge field H01 tilde. And on the overlap, they have to be related by a transition function, which is itself a gauge transformation, lambda A01 lambda inverse minus double lambda lambda inverse. Okay? So that's a general expression. Now, we saw that in each patch, by implying a gauge transformation in each patch, we could set A01 to 0, and we could set A01 tilde to 0. So by doing these extra gauge transformations, we can set A01 to 0, we can set A01 tilde to 0. And then you're just left over with this, right? So with those choices of gauge, the lambda inverse, well, it's a group element, so you get rid of it. You just find that del bar of lambda has to vanish, okay, which means that lambda is holomorphic. So these transition functions, as you go from patch to patch, by these gauge choices, they have to be holomorphic. So there exists a set of transition functions which can be chosen holomorphic. Okay, so that's called a holomorphic bundle. Holomorphic bundle is a bundle where the transition functions can be chosen holomorphic. Okay, now the next one is a little tougher. Okay. So the next condition, the fact that the Kähler trace of f vanishes, that's a little more complicated. So first of all, there's a generic fact about holomorphic bundles. If you take a holomorphic bundle, let's call it V, and you take a holomorphic subbundle, let's call it U. Okay. So you have some Hermitian metric, some curvature on V, and you can restrict that Hermitian metric to U, and you can compute the curvature for U. And it turns out that there's a nice relation. If you then restrict the curvature of V to U and subtract the curvature of U, it turns out that you end up with something that's, positive definite. Okay? So the way that it's expressed is by saying that if you have a holomorphic bundle, then the curvature along holomorphic subbundles always decreases, or at least it's non-increasing. It might be 0. That's a general nice property of holomorphic bundles. It doesn't hold for real geometry, but it's true in complex geometry. Okay? Okay, so now let's try and see what this implies when the Kähler trace of F vanishes. Okay? If the Kähler, so right, so this is the Hermitian-Mills equations. Well, if I then look at a holomorphic subbundle, it's not hard to see that the Kähler trace of U has to be negative or 0, because it's 0 for this guy. It's going to be negative or 0 for any holomorphic subbundle of V. Okay. Now, the expression I have over here, J wedge F, that's actually proportional to the Kähler trace. Okay. So that's going to be some negative definite matrix. And now if I just take the trace of that, the trace here in the gauge indices, I'll end up with something that's negative, or possibly 0, at every point in space-time. Okay? Now I take this and I integrate it. Well, if it's negative or 0 everywhere, and if I integrate it, it will certainly be negative, or possibly 0. Okay? But this here is a topological quantity, which is called the degree of U. Well, it's topological if you fix the Kähler class, that is. Right? So the trace of F, this is actually the first Chern class. The trace of F, so, and, well, it's not, the cohomology class of trace F is the first Chern class, and because I'm matching with J, which is closed, if I change this by an exact form, because J is closed, it doesn't depend on that. Right? So in this expression, trace of F depends only on its cohomology class, and that cohomology class is the first Chern class, which is a topological quantity. Okay, so over here we have a topological quantity, and we've very briefly argued that if U is a subbundle of V, and V satisfies the Hermitian-Mills equations, then the degree of U must be negative, or possibly 0. So this motivates the following definition. A bundle V, a holomorphic bundle V, is said to be stable if for any holomorphic subbundle U of V, the slope of U is smaller than the slope of V. And the slope of U is essentially the degree. It's really the degree over the rank. And the reason why we look at the slope rather than the degree is because I've really implicitly assumed here that I'm working with a simple gauge group. If you work with a non-simple gauge group which has some U1 factors, you have to generalize this equation slightly in terms proportional to the identity matrix. And then you really want to think about the slope rather than the degree. Okay, but anyway, modulo that. So a bundle is stable if U inside V implies that the slope of U is smaller than V. And furthermore, we say that a bundle is polystable if it is the sum of stable bundles with the same slope. Okay? So I briefly argued that with additional assumption of simple gauge group and so on, if you have a holomorphic bundle, then and it satisfies, it has a connection which satisfies the Hermitian-Mills equations, then it must be polystable. So Hermitian-Mills implies polystability. Okay, now, as I said, the slope of U, again, let's look at this. The slope of U is a topological quantity, and this Hermitian-Mills equations, those are differential geometric quantities. Okay, so at first sight, you'd say, okay, one implies the other, but the converse couldn't possibly be true because it's a differential geometric condition. You wouldn't think that it implies this topological kind of condition. You wouldn't think that the topological condition implies this differential geometric condition. But it's true nevertheless. So this is a difficult theorem of Donaldson, Uhlenbeck, and Yau. In fact, Yau calls it one of the most difficult things he's ever done. So the statement is this: if you have a vector bundle V on a Kähler manifold, it's holomorphic and it is polystable. Okay, remember those were the necessary conditions for Hermitian-Mills. And the converse is also true. There exists a unique solution to the Hermitian-Mills equations. Okay, of course unique up to conventional gauge transformations. Okay, so the story here is it's a bit similar to what we saw for Calabi-Yau manifolds. So for Calabi-Yau manifolds, we had this complicated differential geometric condition that you want a Ritchie-flat metric. Okay, and we said, okay, it's impossible to write down a Ritchie-flat metric in closed form, but we just need to check this topological condition that the first Chern class vanishes, and then there's a theorem of Yau that tells you that if that topological condition is satisfied, you can actually find there exists a unique Ritchie-flat metric on your Calabi-Yau manifold. So this is a little similar in spirit, a little similar in flavor. We have a holomorphic bundle, and it has to satisfy this topological-like condition, which says that the slope of every holomorphic subbundle has to be smaller. Okay? So that's necessary, but now Donaldson-Uhlenbeck-Yau tells you that this differential geometric condition, namely the Hermitian-Mills equations, are in fact implied by just having holomorphic and polystable. So again, Hermitian-Mills metrics are basically impossible to write down in closed form. Can't do that. If you now want to construct explicit examples, all you got to do is write down a holomorphic bundle and check that it's slope stable, check that it's polystable, which is much easier to do. Okay, now I'm certainly not going to have time to construct interesting holomorphic bundles for you. I will give one canonical example. There are at least two nice classes of constructions of holomorphic bundles that you might have heard of. So there's the monad constructions, just to take a sequence of line bundles, and then take kernel modulo the image of some maps. Another interesting way to construct bundles is you take a Calabi-Yau which is elliptically fibered, and then you take t-dualities along the elliptic fibers. That's another nice way to, okay, so then you get a system algebraic divisor which you can write down explicitly. Okay, so that's all very nice story, but it's too technically complex to go into here. But just so you know that we certainly know how to write down holomorphic bundles, and then proving that there exists a solution of the Hermitian-Mills equations then just boils down to showing that those holomorphic bundles are polystable. Okay, so here's the canonical example of a Hermitian-Mills bundle. Okay, we just take the tangent bundle of a Calabi-Yau. I've already done this calculation for you previously. If you just take the anti-commutator of the covariant derivative acting on epsilon, that gives you the curvature. Okay, and if you stare at it, that's just the equation FPQ contracted with gamma PQ for the spin connection. Okay, so those are exactly the Hermitian-Mills equations for the spin connection. So the connection on the tangent bundle actually is an example of a solution to the Hermitian-Mills equations. Okay. By similar arguments, any bundle that's associated to the tangent bundle, like the cotangent bundle or anamorphism bundles, those are all also stable to also satisfy this equation. Well, some modification of this appropriate modification of this equation. Okay, so we didn't need Donaldson, Uhlenbeck, and Yau for that. But for these other examples that are mentioned in passing, these monad constructions or the spectral cover constructions, you certainly do need Donaldson, Uhlenbeck, Yau in order to prove the existence of a Hermitian-Mills connection. Okay, now given the time, I think this is exactly 40. No, that's a new topic that's going to take too long. That's not going to be done in 2 minutes. Okay, so I think this is a good point to stop.